Now, each of those four gas laws that we just discussed have one very significant limitation, and that is they can only look at two of the properties of a gas at a time. So if we're using, say, Gay-Lussac's law with pressure and temperature, the only way that that law works is if the other two variables, volume and moles, remain constant. Boyle's law with pressure and volume only applies if moles and temperature remain constant. And so in real life situations, it's pretty rare that only two of the variables are changing. For example, back to our potato chip bag example, when we go up to Lake Tahoe, the pressure decreases as you go up in elevation, but also the temperature will decrease and the volume of the bag will change. The only thing that will remain constant is the number of moles because the bag is sealed. So now we have three variables changing, but none of our individual gas laws can deal with more than two. So the good news is you're not ever going to have to use those four individual gas laws because they're so limited. What we're going to do instead is to combine them. We're going to put those together in what's known as the combined gas law. The combined gas law incorporates all four variables, pressure, temperature, volume, and moles, into one equation. So this is the combined gas law. You notice we have P, V, N, and T on both sides. And if you look at it closely, we have P1 V1 equals P2 V2. That was Boyle's law. We have P1 over T1, P2 over T2. That was Gay-Lussac's law. V1 over T1, V2 over T2, Charles' law. And finally, V1 over N1 and V2 over N2, that's Avogadro's law. So all four of those laws are incorporated into this one equation, and so we can have even all four of the variables changing at the same time, and the combined gas law can still manage that. So let's take a look at a sample problem here. Let's suppose we have a flask of helium, and we know its initial pressure, 15.5 psi, and we're going to change its temperature from 20 Celsius to 100 degrees Celsius, and we'd like to know what the final pressure is in the flask. Well, since the only two things that are changing are pressure and temperature, we could use Gay-Lussac's law, but we don't need to, because the combined gas law can handle everything. So the first step in doing a combined gas law problem is to eliminate any of the properties that are not changing. If we take a look at this, we can see that there's no volume is not mentioned and moles is not mentioned, which means those two properties are not changing. So we can cross those out. So we can take the two volumes out of the equation and the two moles, and why, lo and behold, we're left with P1 over T1 and P2 over T2, and that's Gay-Lussac's law. We didn't have to memorize Gay-Lussac's law. It simply dropped out of the combined gas law when we needed it. Our second step is to rearrange the equation to solve for the unknown. Now, unfortunately, this is not an algebra class, so I'm not going to be spending a lot of time reminding you how to do algebra. So you might want to make sure you refresh your memory. But basically what I've done here to solve for P2, I've simply moved T2 across and up, and that gave me P1 T2 over T1, which I have here. And then finally, our third step is to plug in the values that were provided in the appropriate units. And in particular, that means make sure your temperatures are in Kelvin, not in Celsius. So we can plug in our 15.5 psi. The 100 degrees Celsius for T2, I simply add 273 to that, and it gives me 373 Kelvin. And I add 273 to my 20 degrees Celsius to give me 293 Kelvin, and I come out with a new pressure of 19.7 psi. So not surprisingly, an increase in temperature led to an increase in pressure. All right, let's do another example problem here. This time we have a balloon which will start out in Stockton, and that balloon has a pressure of 1.1 atmospheres, a temperature of 31 degrees Celsius, and a volume of 535 milliliters. We're going to take a drive up to Lake Tahoe with our balloon, and by the time we get there, the pressure has dropped to 0.92 atmospheres and the temperature to 22 degrees Celsius, and we would like to find out what the new volume of the balloon will be. Well, we have three different variables changing here: pressure, temperature, and volume, so we can't use any of our four basic gas laws, which means we will have to use the combined gas law. Our first step, as always, is to eliminate anything that isn't changing. And of course, in this problem, pressure, volume, and temperature were changing, but the moles is remaining constant because it's inside a sealed balloon. So we can get rid of N1 and N2. Our second step is to rearrange the equation. And again, I'm not going to do a lot of algebra refresher for you, but I will show you a little shortcut that I've been using since I was in high school. Whenever you have an equation like this where there's a fraction, you can move any variable you want diagonally to the other side of the equation. That's perfectly mathematically allowable. So since I want V2 to be by itself, I can move P2 diagonally down. That's why it ended up down here. I can move T2 diagonally up, which is why it ended up on the top, and I end up with my correctly rearranged equation. There's a YouTube video that also does some refreshers in how to rearrange the gas laws, and I'll add that to our lecture materials for Chapter 13. So our third step, as always, is to plug in the values, making sure, of course, they're in the appropriate units, and that usually means I'm talking about making sure the temperatures are in Kelvin. So we have a P1, our initial pressure, 1.1 atmospheres, V1, our initial volume, and T2, our final temperature, which was 22 Celsius. We simply add 273 to that to get 295 Kelvin. Our final pressure in Lake Tahoe was 0.92 atmospheres, and our initial temperature, 31 Celsius, that converts to 304 Kelvin, and that gives us a new volume of 621 milliliters. All right, let's do one more practice problem with the combined gas law. So this time we have a cylinder of nitrogen with a volume of 10.6 liters, a pressure of 2200 psi, and a temperature of 25 degrees Celsius. And I'd like to know two things this time: how many moles of nitrogen are in the cylinder, and how many pounds of nitrogen. So let's start out like we always do with our combined gas law, and we'll cancel out any properties that are not changing. Well, holy cow, nothing's changing, it looks like. We have one pressure, one temperature, one volume, and so by the time we cancel out the properties that aren't changing, we've actually canceled everything. All we're left with is an equal sign. So it turns out that a problem like this cannot be handled using the combined gas law. The combined gas law has an initial and final value for each variable, which means it can only deal with things that are changing. So how do we deal with a problem where things aren't changing? We just have a cylinder of nitrogen and nothing is happening to it. It's got a fixed volume, a fixed temperature, a fixed pressure, and a fixed number of moles. So we're going to have to make some adjustments to our combined gas law in order to be able to deal with this kind of problem. So here we have a tablespoon. If I were to measure the pressure and volume and temperature and the number of moles of air in that tablespoon, I could plug them in for P, V, N, and T, and I would get a certain number, whatever it would happen to be. I could do the same thing with the helium in this balloon. I could measure the pressure, volume, moles, and temperature of helium in this balloon. Now it's much larger, but will I get the same value? Is it still going to give me that same value of X? The answer is yes, because the combined gas law says that P1 V1 over N1 T1 must equal P2 V2 over N2 T2. Now, this probably seems a little counterintuitive. How could that much larger balloon have the same value of X as our small tablespoon? And if you think about it, it's pretty simple. The pressure in each of these is essentially the same. There's very little difference in pressure in the balloon. On the temperature, they're both at room temperature. So really the only big difference is the volume and the number of moles. Well, the volume of the balloon is clearly much larger than the tablespoon, but the number of moles is also much larger. So if the volume were, say, 1,000 times bigger and the moles were 1,000 times bigger, those would cancel out. And so X will come out to be the same. We could go even larger and have a huge hot air balloon, millions of times bigger. Yet if we measured its pressure, volume, moles, and temperature, it would still come out to give us this same value. So no matter what kind of gas you have, no matter how much of the gas you have, if you measure P, V, N, and T, it always gives you the same value. In science and math, whenever we have a number like that that's always the same, we refer to that as a constant. For example, you're familiar with pi, 3.14. That is a constant. If you take a circle, any size circle, big or small, and you divide the circumference of the circle by its diameter, it's always 3.14. That's why it's a constant. In the gas laws, that value of X that we always get from PV over NT, we call that constant R. So that is the gas constant. If we take this equation, so now what we've been able to determine is not only do all PV over NTs equal each other, they also equal the same thing, which is R. We can simplify this a little bit by cross-multiplying it, and so we don't have to deal with any fractions. And we get a new equation that says PV equals nRT, and that is known as the ideal gas law. It's called the ideal gas law because it only works when gases behave very nicely, which most of the time they do. As long as your pressure is not too high, the gases tend to follow this law very efficiently. Now, what is R? How do we figure out the value of R? Well, R is called the ideal gas constant. So it appears in the ideal gas law. It's called the ideal gas constant. And to calculate it, we would simply need to take a sample of a gas. Doesn't matter, it could be the tablespoon, the balloon, or the huge hot air balloon. Measure P, V, N, and T, and that would give us the value for R. Now, will the value of R always be the same number? You would think so, but let me ask you this. How tall am I? Is my height 6, 72, or 2? The answer is it's all 3, because I didn't put any units in there. I'm 6 feet tall, I'm 2 yards tall, I'm 72 inches tall. So the value of R could vary depending on the units that we use. Now N, of course, is always moles. We have no choice there. Temperature is always Kelvin. But pressure and volume, there's a lot of different units you can use to measure pressure and volume. So chemists figured out a long time ago that they needed to use particular units for R so they would get the same value. So it was decided that we would measure the pressure in atmospheres and the volume in liters. I mean, you could have used quarts and PSI, but if you did that, you'd get a different value. So in order just to keep things from being confusing, all the chemists said, you know what, let's all agree to always make our pressure in atmospheres and always make our volume in liters. And if you do that, if you plug in these four values for a sample of a gas, you're going to end up with 0.082. And then, of course, since we measured pressure in atmospheres, volume in liters, and in moles and T in Kelvin, we have to write those 4 units down. It tells people, oh, these are the 4 units you used when you measured your value of R. So let's go back now to that problem regarding the cylinder of nitrogen. We have only one volume, one pressure, and one temperature, and whenever there's only one value of each variable, that means we have to use the ideal gas law, the PV equals nRT. We have a pressure, we have a volume, we have a temperature. Of course, R is given, so the only thing that we're missing is N. And so whenever you have one unknown in your equation, it's easy to solve for that. So the first thing we'll do is we'll rearrange our equation. So if we move RT over and down, we get N equals PV over RT. For the pressure, of course, because we've decided that R is always going to have units of atmospheres, we can't put in 2200 psi. So we're going to use our conversion we learned earlier, and we're going to change our psi into atmospheres, and that's what we'll want to plug in for our pressure. Same thing with temperature. We can't plug in Celsius because the gas laws are always in Kelvin, so we're going to convert that to Kelvin, and we'll plug that in for our temperature. The volume is already in liters, so we're okay there. If it weren't, we'd have to change it, but it's already in the appropriate units. So we plug our numbers in, and we end up with 65 moles. So there are 65 moles of nitrogen gas in that container. Now the second question asked how many pounds of nitrogen. So how do you go from pounds from moles to pounds? Well, this is taking us back to chapter 9 when we used molar masses to relate grams and moles. So if we wanted to get from moles to pounds, the first thing we would have to do is convert it to grams. Don't forget that nitrogen gas is N2, not just N, so it's going to be 28 grams per mole. And then, of course, we can change grams into pounds, and we end up with 4 pounds of nitrogen in this cylinder. So the key thing is, whenever you're doing one of these gas law problems, first thing you have to ask yourself is, should I use the combined gas law or the ideal gas law? And the choice is very simple. If things are changing, if you have more than one value for any of the variables, then use the combined gas law where there's a P1 and a P2 and so on and so forth. If you have a problem like this, where there's only one value for each variable, then we have to use the ideal gas law. All right, let's try another problem using the ideal gas law. This time we want to find the volume of 1 mole of helium. Well, there's a problem. How do we figure that out? Because we don't know all of the variables. The volume of a mole of helium could be a lot of different things. What else affects the volume of a gas? And of course, the pressure and temperature, so our answer will depend on what the pressure and temperature are. So you can't simply say, what's the volume of a sample of a gas? Because if you increase the pressure, the volume goes down. If you decrease the pressure, the volume goes up. Same thing happens with the temperature. So chemists realized early on that in order for us not to be confused when communicating with each other, it would be helpful to agree to use a particular temperature and pressure so that everybody was on the same page, apples and apples. So they decided to come up with a standard temperature, and pressure. Some logical and easy to remember value of temperature and pressure that everybody could use. So for standard temperature, they chose 273 Kelvin, which is the freezing point of water. That's a nice, easy thing to remember. For a standard pressure, they chose 1 atmosphere. It's simply the pressure of the Earth's atmosphere at sea level. And of course, both of these are in the units that we use in the ideal gas law. So standard temperature and pressure are simply referred to as STP. So we could re-ask our question now and say, what is the volume of 1 mole of helium gas at STP? Okay, so now we know our pressure and temperature. So we can take our ideal gas law and rearrange it. So in this case, we're trying to find volume, so I simply move the pressure over and down to give me this new equation. Then it's a matter of simply plugging in the values. So we have 1 mole of helium. We have R, which is always the same thing, 0.082 liters times atmospheres over moles times kelvins. And our standard temperature is 273 Kelvin, and of course, our standard pressure would be 1 atmosphere, and that comes out to be 22.4 liters. So that's the volume of 1 mole of helium at standard temperature and pressure. Now, what is the volume of 1 mole of oxygen gas at standard temperature and pressure? Well, if we take a look at the ideal gas law once again, it's still 1 mole, it's still standard temperature, still standard pressure. In fact, all the variables are the same. So it didn't really matter whether it was oxygen or helium or any other gas. No matter what the gas is, it's still going to come out to be 22.4 liters. So whatever the gas is won't make any difference. The thing about the gas laws, both the combined and the ideal gas law, you'll notice there's never anywhere to plug in the identity of the gas because it doesn't matter what the gas is. The kinetic molecular theory just looks at all gases as tiny little particles bouncing around, and it doesn't matter what the particles are made of. So that 22.4 liters, that's known as the standard molar volume of the gas. It's the volume of 1 mole of a gas at standard temperature and pressure. Have you ever wondered why helium balloons float in air? You've probably heard people say that, oh, helium is lighter than air. Well, that's not exactly correct. If you put a penny in a swimming pool, it doesn't float, it sinks. Does that mean that the penny is heavier than all that water in the pool? No, of course not. That penny weighs very little. The key is the penny sinks because it's denser than the water in the pool. So helium balloons float not because helium is lighter than air, but because it's less dense than air. Now, as we learned back in the very first week of the semester, calculating density requires only 2 things, a mass and a volume. Does the density of a substance depend on the amount of material you test for mass and volume? And the answer is no. The density is going to be the same no matter how much you have. A gallon of water has a density of 1 gram per milliliter. A swimming pool of water, it's still 1 gram per milliliter. So we can choose whatever amount of helium is convenient. And the most convenient amount to choose would be 1 mole. Because a mole of helium, we can look up the mass right on the periodic table. We can make volume easy as well. If we decide to use standard temperature and pressure, we know that the volume of 1 mole of any gas will be 22.4 liters. So by choosing 1 mole of helium at STP, we know that it's 4 grams, comes from the periodic table, and the standard molar volume is 22.4 liters for all gases, and we get our density of 0.18 grams per liter. We can do the same thing with air. Now, the molar mass of air is not something you can get directly from the periodic table because air is a mixture, mainly of nitrogen and oxygen. Nitrogen N2 has a molar mass of 28, and oxygen O2 has a molar mass of 32, which means the average will have to be somewhere between 28 and 32. You don't have to worry about how to calculate that, but the fact that nitrogen is more abundant in air, the average comes out closer to 28. Turns out that it's 29 grams per mole. So that's simply a number you're going to want to remember because you'll be using that on problems in the future. So 29 grams per mole, 22.4 liters, we get a density of air of 1.3 grams per liter. So clearly, helium is indeed less dense than air. Now, helium isn't the only gas that's capable of floating a balloon in air. Do you think you could list all of the elements that would float in air? Well, on the periodic table, there are 11 gaseous elements. So how do we figure out which of those would be suitable for floating a balloon in air? Well, essentially, any gas that has a density of less than 1.3 grams per liter would be capable of floating a balloon in air. But we can make it even simpler than that. We don't really have to calculate the density because all gases have the same molar volume of 22.4 liters. So essentially, any gas whose molar mass is less than 29 is going to have a density less than 1.3 grams per liter. Hydrogen, for example, H2 has a molar mass of 2, definitely going to float, even better than helium does. Helium, of course, is on our list. It has a molar mass of 4. Neon, with a molar mass of 20.2, that's less than 29. And even nitrogen, it's just barely lighter or less dense than air. So a nitrogen-filled balloon would float, it just wouldn't float very well. Now, any gas that is less dense than air can be used in a balloon. It doesn't have to be an element, it can even be a chemical compound. Now, when I was about 14 years old, I got really interested in balloons. But unfortunately, on my 50 cents a week allowance, I couldn't really afford a tank of helium. All that money went for candy and comic books. So I figured out I could make balloons out of hot air. Hot air is actually less dense than cold air. When you heat air up, the air expands, so it takes fewer molecules to fill up a space, and therefore there's less mass. I started doing this at about 14 years old. It took me a few months, but I finally figured out I could make balloons out of old dry cleaner bags I got from my mom and a little teeny aluminum foil container of alcohol which would burn, and it would heat the air and the balloons would float. Now, when I got to college, I had a friend that used to do this with me, and he always liked to make things bigger. So we began to make larger and larger balloons. This was our second biggest one we ever made. It was 38 feet tall and about 16 feet across, and it flew about 10 miles before it came down on the roof of a shopping center in Omaha, about 10 miles away. So hot air worked great, but I always wished I could have helium to fill a balloon with. Well, when I took chemistry in high school, I began to realize that there were chemical compounds that were actually less dense than air. So, for example, carbon monoxide, CO, has a molar mass of 28 grams per mole. Now, carbon monoxide, very dangerous stuff. You definitely would not want to be messing with that. Ammonia is a gas. It has a molar mass of 17 grams per mole. That would float very well. But again, ammonia is a pretty toxic material, not the kind of thing you want to be messing around with. When I took chemistry in high school, I got to the end of the school year and we were studying chemical compounds made of carbon. And I came across the formula for methane, CH4, and I immediately realized, methane has a molar mass less than 29. That stuff ought to float. If only there was an easy place one could get methane. Well, luckily in my chemistry book, it mentioned that natural gas, the major component is methane. So I went home that night, got a garbage bag from my mom, taped it shut, brought it back to the lab the next day, and I filled it full of natural gas, and lo and behold, it floated. So during that year, I made bigger and better balloons, culminating at the very end of the school year, 1973, I made a 19-foot tall balloon full of natural gas made out of garbage bags in the shape of the numbers 73 and launched it.